Okay. So let's finish the proof of Edge theorem that we started with the last time, and then we basically proved. So we had this claim that told us that for every k graph H, when we consider the homomorphism density, then we have this following inequality. So when we embed the complete k-partite k-uniform hypergraph with partition classes of sizes m1 to mk into H, then its homomorphism density is greater or equal to that when we embed single edge and raise it to some power. Okay, and we finished the proof of this the last time. So let's now prove our theorem. And just to recall, our theorem was that we have that the Turán density of a k-graph is 0 if and only if it's 0 if and only if f is k-partite. Okay, so let f be such a k-partite graph. And let's have some epsilon given. Also recall that we proved one direction, right? So we proved that if f is not k-partite, then the Turán density is greater than 0. Let now H be a k-graph in vertices with epsilon density and it's assumed that our n is large. Okay, and now we use this claim for this H. So the homomorphism density of this H is greater or equal to that of a single edge. Raised to this power. Okay, so first note that this claim holds for all mi here. So we can make those mi so large that our f is contained in there. So with m1 to mk so large that f is contained this. And there we use, of course, that our f is k-partite. Okay, so now on this side, as we also used the last time, this is basically just, so if we count the homomorphisms here, this is basically just the number of edges in H with this k factorial term in order to include all the orderings. So we have this. Is k factorial times the number of edges of H, and then divided by just our norming factor for this, so that was n to the sum of these the sum of the vertices here, which is just k, n to the k, and then we raise this again to the power of the product of these mi. Okay, so now the number of edges in our H was this because it has epsilon density, so it's epsilon times n choose k. So roughly for n large, we can say that that's maybe still greater or equal to epsilon half when we divide by n to the k. When we divide by n to the k divided by k factorial. So this is greater or equal to epsilon half to the product of these n. Okay, but this is now just a lower bound on the homomorphism density of this k graph in our H.
So it should be M1 until the last line reach from K sub M1, M2, not the edge, right?
No, this is an edge. This is just this part here. But the power.
Right, yeah.
Yeah.
Oh.
Yeah. So by definition of this homomorphism density, this implies that if we now just look at the number of homomorphisms from K uniform into our H, then this is greater or equal to this epsilon or epsilon half raised to this power. And now times the number of all possible maps from here to here. So this is n, the sum of the mi. Okay. So and now the only thing that we need to argue is that we actually find a copy of this in H, right? Because then F is contained in this K graph, and therefore F would also be contained in H. But we can do that because we know now that we have this many homomorphisms. But how many degenerate homomorphisms do we have? So how many non-injective ones? Well, at most, some constant times n to the power of this minus 1. So now that the number non-injective homomorphisms from K M1 K to H is big O of n plus sum of the mi minus 1. And therefore we have an injective homomorphism and then a copy of this one. So that's okay. Any question about this? If not, then we would move on to what we call supersaturation. Which is actually also very related to this this proof here, but usually the theorem that we call or that we refer to as supersaturation is the following. So we know that by definition, if our n is large enough, and we have a K graph H that has density above the Turán density of some K graph F, then we know that we contain a copy of F. But what supersaturation tells us that if we're an epsilon above the density, then for large n, we actually have many copies. So given K graph F and some epsilon greater to 0, there are some C greater to 0 and some and 0 such that every K graph H on n greater or equal than 0 vertices with at least pi f plus epsilon density contains at least this C times n, choose the number of vertices of F, copies of F. Okay, so we have the right order of magnitude of copies. So how do we prove this? So basically, the idea will be that we take some n0 so that we know that the extremal number of F on n0 vertices is below pi of F plus epsilon half times n choose n0 choose K. So that means that we know that if whenever we have a set on n of n0 vertices and we have that number of edges, so with an epsilon half here, then we contain a copy of F. And then so imagine that this is our whole H, and now we look at all these sets of size n0. And since globally we have this density, and we even have this epsilon space, so when we go down to epsilon half, we know that we need to have many sets of size n0, which have this which have more edges than the extremal number on n0 vertices. But that means that in each of these we find some copy of F. And then there's of course an overcounting happening, right? Because every potential copy of F is contained in several n0s, but all this overcounting works out. So let n0 be so large that the extreme number n0 F, and maybe I just simplify it by n0 choose K, is at most F plus the epsilon half. Yeah, and also recall that the last time we showed that this thing here is monotone. We don't need it here, but it's so good to recall because we need it at other points. Okay, so now that H be a K graph on n vertices, and denote every set X of vertices EX by EX, number of edges that H sees on X. Okay, and further, let's also assume, of course, that our H has the right edge density. Okay, and now let's refer to those where we have many edges so that we know that we have a copy of F as good. So those sets X of size n0 is called good. Oh, X good. Okay, let's say just any subset we call good if the size of X is n0 and the number of edges on X is at least pi of F plus epsilon half. It's n0 choose. Okay. So again, because we took this bound for our n0, so we know that each of these good X will contain a copy of that. But first we want to know the number of these, right? That's what I said here. We want to count the number of copies of F eventually, but for that we want to say that there are many of these good sets, because then by double counting there will still be also many copies of F. So okay, and so we want to, on the one hand, just sum over all sets of size n0 and count the number of edges on this set. So on the one hand, how often do we count each edge of H? So here we get the number of edges in H, but now we count each edge that many times in how many ways we can extend it to a set of size n0. And how many ways are there? Yeah, how many times we can extend that edge to the set of size n0. So we have still n minus k vertices left, and we still want to choose n0 minus k vertices. Okay, so this is the number of times that each edge of H gets counted in this sum. Okay, but then by our bound on the number of edges of H, we get that this is n minus k n0 minus k times this I F plus epsilon. Okay, and on the other hand, we can split this sum up into those X which are good and those X which are not good. So okay, and so how many edges do we have in any such X? At most, all the edges on an n0 set, right? N0 choose k. So times the number of good. I will just denote it like this. And on the other hand, for these not good sets of size n0, we cannot bound the number of them. So maybe we have n choose n0 of those, but we definitely know that they have at most this number of edges. Okay. But this gives, because these binomial coefficients, this product here is equal to the product of these binomial coefficients. So we get that we have pi F. So we subtract that side. So we still have epsilon half times n0 times n0. Okay. Nice. Okay, so is it clear? We just subtract this part from the left side, since this product of binomial coefficients is the same as the product that we see there. We are left with epsilon half times this product. And then here we also see this factor, so we can cancel out that factor to get our lower bound. On the number of good sets. Okay, so again, this is already looking promising, because we showed that the number of good sets, which are sets of size n0, are of the right proportion. So now again, by double counting, so let's sum over all sets of size n0. And so x set of size n0. And let's look at the number of copies of f in H induced on X. Okay. So on the one hand, this counts the number of so on the one hand, we just know that this is greater or equal to the number of good X. And on the other hand, we know that with this, we definitely count each copy of F in H. And again, we overcount, right? So this is the number of copies F in H. But for each copy, again, right? So this is a set of VF vertices, and we want to extend it to a set of size n0. So we have n minus VF, choose n0 minus VF. Okay, and here we use our low bound epsilon half. And this gives that the number of copies F H is at least epsilon half magnitude n0 divided by n minus F 0 minus Vf. Okay, and now we can again use that this sort of product here is equal to this product, to say that, so what we wanted here is NVF, and we get epsilon half and epsilon half, and here n minus
yes, and 0 choose VF.
Yes. Yes, yes. Okay, and then so this this part we can define as our C. So because this N0 and this BF are just some constants that we chose in the beginning, so this C is also some constant that we choose. Okay. So why is this nice? So for instance, one corollary that we have from this is that we can know that the Turán density of a blow-up is the same as the Turán density of the graph itself. So for every F, a graph F, F and integer T, the Turán density of F is equal to the Turán density of Ft, where Ft is the T blow-up of F. Okay, so it's obtained from F by replacing every vertex with a set of T vertices, which are all copies of the original vertex. So each of these is of size T, and replace an edge for any K vertices across K partition classes, which correspond to the original vertices in F. So K graph. Paint F by replacing every vertex. Okay, how do we prove this? So given F, E, and epsilon, let's choose some constants. So these are our initial constants, and now we want to choose some N0 and some Xi, which work with respect to supersaturation. So this Xi and then some N0 -1 should be much smaller. And here we also want to have maybe some capital T -1, which we will see in a moment. And all those should be much smaller than our N1, which is actually then the size of the K-graph H, for which we say that that we can find this blow up if we have the right density. So let H be a K-graph with let's say on n version n greater equal n1 vertices with the number of edges H greater equal to I F plus epsilon times H is K. And we want to find a copy of our T blow up of F in H. Okay, so by supersaturation, in this earlier theorem, we know that H has at least C times n choose BF copies of H of F. Okay, and we will now define an auxiliary hypergraph where we place a copy, where we place an edge for each copy of F. So let H tilde be an auxiliary graph, and it has this uniformity now, the number of vertices of F. On the same vertex set as H, whose edges are the copies of H. Okay, so more formally, the vertex sets of the copies of F. So then the number of edges of this H tilde is greater or equal to this C times n choose BF. And it is a BF graph on n vertices. So now if our n was large enough, meaning our n1 was large enough, then by the result from last lecture and the beginning of this lecture, we know that every VF graph which is k-partite is contained in here. So I introduce this on. We know that, and that's why we chose this capital T. We know that we now have the complete VF uniform and VF partite graph on with partition classes all of size capital T. We know that this is contained in H tilde. So we're almost done now. The problem is just that right, so we have our partition classes and all these edges, and each of the edges is a copy of F. So this basically looks like a blow up of F. But the problem is that our F is not necessarily complete. So in particular, it's not necessarily symmetric. So it might be that for this vertex, this plays the role of a different vertex in its copy of F than the vertex next to it. Okay, and that's why we need to sort out the right orientation with respect to our vertex classes. So each edge in this chain TBF has one of VF vectorial orientations with respect to the vertex classes of this KTT. Okay. So, but this means that now by a Ramsey result, so it's of course not exactly the original Ramsey, but essentially the same argument. We know that because our lowercase t is much smaller than our capital T, we know that for one of these orientations, which we think of as colors, we find a monochromatic KTTT with T lowercase. So the Ramsey. Here is some K T whose orientations same. Right, so if this still seems a bit strange here with the orientations, think of the vertices of F being enumerated from 1 to PF, and we want to ask which so this partition class, which role should it play? Should it be the role of vertex 1 or the role of vertex VF or something in between? And so this gives us the colorings of the edges of this KTTT, and then we have a monochromatic KTTT with the smaller t. Okay, and then this eventually corresponds to our blow-up of F. Okay, any questions about this?
Can you explain that part, like E to the -1?
This?
You know, what does this mean?
So this is just the hierarchy that we want to choose, right? So we start with these, our F that's given, our T and our epsilon. And then with those given, we want to choose these. And then once we've chosen these, we want to choose this. And we want to choose it such that, so right, some are integers. This is an integer, this is an integer, and these two are, oh, sorry, this one's also something. If that's the question. So, and this. So we want to choose, given epsilon, we want to choose this t to be very large, right? But again, what that means is that because epsilon is very small, so t to the -1 should be even smaller than that. Okay, so you can just rephrase these as given all these, they exist some these. And eventually we want to choose this N1 to be very, very large with respect to everything that we chose before. Is that clear? Okay, so let's close this part with some remark. So one is in this way we can also prove Edish-Shimonovitz actually even in an easier way. So an easier argument. Edish-Shimonovitz. Right, because for that one, we just know that, oh, if we have if we have this density, and we basically with this chromatic number, that just means we want to find a blow up of a clique of the respective size, right? And then we know that if this is the chromatic number, we can embed our F into that. And so here we will just say that, oh, by Turán's theorem, we know that we contain a clique of a certain size. And then here our auxiliary hypergraph is just formed by placing cliques of that size. So we don't have that issue with the orientations. So if the orientations were confusing, then maybe just be happy with proving edge stone monoliths. Okay, the other argument, the other remark here is, so we say that some K graph H is F free if there's no homomorphism from F into H. And then, of course, we can define our extremal number in the same way as we defined the extremal number before, and then we can define the Turán density with respect to this. So instead of the normal extremal number was just we were talking about F-free graphs, and now we're talking about F-hom-free graphs. So the extremal number with this lower index home and the Turán density with lower index home can be defined and this argument also tells us, so this argument with the blow-up also tells us that these numbers are the same. So and this can often be quite useful because now we don't need to care about some degenerate forms, and to see an an application of that, and also because we want to see a different type of argument now. We'll look at the following example. So now we'll start to actually determine some Turán densities, because even though we saw the last time that some of these really simple looking examples are still open, but actually we can determine the Turán densities of some hypergraphs. So the Bolobash is a graph on 5 vertices with edges 1, 2, 3, 1, 2, 4, and 3, 4, 5. Okay, so what does that look like? We have 5 vertices. Okay, and so Bolobash showed the following theorem. Density of, when we forbid both B and the K4 minus, then this Turán density is 2,9. So one thing is that for a family, again, we can define similarly as here. Also for a family, we can just define the extremal number and then the Turán density analogously. Right? We just say that, oh, now we look at the maximum number of edges that some K graph on some number of vertices can have without containing any member of the family. Okay. But now also because of this result, we actually have that this implies that the Turán density of this K graph by itself is 2,9. So So why is that? Because the K4 minus is a homomorphism of this one, right? So if we see a K4 minus, so where this is the apex, the vertex that's contained in all three edges, then we can just map this vertex to this vertex or this vertex, and then we'll so we embed these. Let's say this one goes here, this one goes here, 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 and this one we also embed here. Okay, so let's prove this. And I should also say that as we will sort of see in the proof, but we will not go through all the calculations, Bolbosch actually determined the extremal number here. So at least for Lagrangian. So for the lower bound. Consider the balanced complete tripartite graph. Okay, so just this where we have all the edges of this form. And this does not contain B nor the K4 minus, and the density of this one is 2,9. So let's say on n vertices. And we want to denote the number of edges in this complete balanced tripartite 3 graph by Bn. Okay. So we perform, or we show by induction on n. Definitely B4 B minus 3 graph. Satisfies that the number of edges is at most Bn. Okay. So the induction start can be checked by hand. And so for the induction step, first let's know that when we have some 3 vertices which are not incident to many edges, we can just delete these, because then we are left with still many edges on the remaining n minus 3 vertices, and we imply induction. Yeah, so this maybe should be n minus 3. So note that if 3 vertices are incident to less than Bn minus Bn minus 3 edges. Oh, at most this many edges, deleting these vertices leaves us with a K-graph, 3-graph on n minus 3 vertices with this minus this plus Bn minus 3 edges. So if our H had more edges than Bn, then also this new 3-graph on n minus 3 vertices will have more edges than Bn minus 3, and therefore by induction contains B or a K4 minus. Okay, so this part clear. Just if we have some vertices which are incident to few edges, we delete these, apply induction to the remaining remaining 3-graph. And this is a general argument that we can do. So we will see after this in some small observation that we can basically always assume that we have some minimum degree condition. Okay, so here we delete 3 vertices, but a similar thing could also be done for just a single vertex. So whenever we have a vertex of small degree, delete that vertex, we're left with a 3-graph on n minus 1 vertices with still quite many edges. Okay. So we may assume that each triple of vertices is incident to at least Bn minus Bn minus 3 plus 1 vertices. And this, so I will not show this calculation, but I mean, this is a very explicit number, right? It's just, yeah, you can count it for this graph. This is just the number of edges in this balanced tripartite graph. So this can be calculated to be equal to the extremal number for 2 uniform K4 on n vertices minus n plus 1, and then this plus 2. So what can we do with this? We now want to look, and we take some edge out, and take some edge, and we basically want to look at the link of this vertex, and if we see, so this thing should somehow hint to the fact that we will find something like a K4 in this. And note that if we can find a K4, where all these three different matchings that we have in there belong to one of the so maybe the blue belongs to this vertex, the link of that vertex, the orange one to the link of this one, and the white one to the link of this vertex. Then what we have is that on these 7 vertices, any 2 of them are contained in an edge. And as we will argue in a moment, whenever 2 vertices are contained together in an edge, their links must be disjoint. So we will have 7 vertices whose links are pairwise disjoint. But also, because of this thing, we know that whenever we take 3 vertices, so a set of 3 vertices, then the sum of the edges and their links must be relatively large. Okay, and that will then give us a contradiction to the fact that these links should be disjoint. So note that since H is B equal to B minus B, any 2 vertices which lie in an edge together have okay. So why is that? So we have these vertices which line some edge. And now when you're telling me that the links of these, let's maybe denote the links by this blue edge, are not disjoint, then either we have this thing, which implies that that this is an edge and this is an edge. Okay, but this thing is our B. And then you might also say, okay, maybe this edge that they share in the links contains that vertex, but then will be a K4 minus. Okay, so we have that these must have disjoint links. Further, since H is K4 B minus B, we also have that. So again, when we take some edge, then and we look at a vertex outside, with how many pairs of this edge can this vertex lie in an edge? It's again just with one, or it is just with one, because otherwise we would have three edges on 4 vertices, which is a K4 minus. So for every edge x, y, z, and any vertex outside x, y, z can form an edge with at most 2 of the pairs. Sorry, 1. With at most 1 pair and x, y, z. Okay. So now let L be the graph on V minus X, Y, Z. So we take some edge X, Y, Z. With or formed by the union of HX, HY, and HZ, right? So these again with the links of the vertex of H with respect to the vertex X with respect to Y and Z. Okay. So by the above, we have, so we want to count the number of edges in this L. And so one thing is that each of the edges which are in one of the links of X, Y, or Z will appear in this. And they would overcount, right? Because those links must be disjoint because X, Y, and Z are all contained in an edge together. So we get in principle, the number of edges incident to this triple, but then we have to be a little bit careful. But let's first write that. So why do we have to be careful? In these edges, one thing is we also counted the edge itself, right? The edge itself is also incident to it. So you get a -1 for that because it will not appear in this graph L. And now also those which are formed by taking a pair of the edge and one vertex outside, those we will also not count, right? Because they will not appear in any of the links. So, but how many do we have of those? So again, if we have X, Y, Z, X, Y, Z, what I said is that we don't count these sort of edges. But these were exactly the edges that we argued before, that for every vertex outside, it can be neighbored to at most one of the pairs. So the number of these edges is at most the number of vertices outside. So n-3. Okay, and now this thing can be calculated to be xn -3 A2 for small. Okay, so that is looking good. Because that will tell us, or that tells us that this graph L will contain a K-form. Let me write it here. Thus, K4 it's in L. Say on vertices A, B, C, D. And so we're almost we've almost arrived at what I described here as the plan. The only thing that we need to argue is that we see this sort of matching. For that, we will remark that we cannot have a triangle in this graph L such that two of the sides of the triangle come from the same link. So note that all edges in triangle in L come from different things. Okay, and why is that? So if we have a triangle in this L, and two of these come from the same link, then what does that actually mean? So they come from the link of this orange vertex. so this means that if we call this one Bx, this is A, B, C. This means that in the 3 uniform world, so with our actual hypergraph, we have X, A, B, C. But also this thing is still contained in some edge. And that edge might either be formed with X, which would give a K4 minus, or it's formed with some of the other vertices outside here, which would give the B. So okay, but then that means that our on this ABCD we see this picture. And this means that that any 2 vertices of these 7 vertices lie in an edge together, which means that their links are disjoint. So all vertices in X, Y, Z, A, B, C, D have pairwise disjoint links. Okay. So now, right, because of the point that I made before, that whenever we have 2 vertices which lie in an edge together, they must have disjoint links. Okay, so now let's look at the following sum. So we go over all alpha, beta, gamma in the 3 subsets of these 7 vertices. And we sum the edges of H alpha, the edges of H beta, and the edges of H gamma. Okay. So on the one hand, we know that this thing must be at least the number of edges incident to alpha, beta, gamma. Because every edge that's incident to one of these will appear in one of these links. Because here we're looking at the complete link. So we have this bound from before on that, right? So this is at least 7 choose 3 times this 4. Minus n is 2. And on the other hand, how often do we count each link here? So each link appears for each of the triples. So for 6, choose 2 other times. We have 6 choose 2 is the sum for the edges H alpha. Okay. But now we divide this. And get this. But this thing here is more than n choose 2. But we said that these 7 vertices almost have pairwise disjoint links. Okay, and each edge in the link of these is one of the pairs of on n, so we cannot have more than n choose 2 those. So this one more example of this, or there are several more, but maybe let's talk about one more. Example where we can determine the Turán density explicitly. But for that it would be useful to have this observation that I mentioned before, that we can always assume that we have some minimum degree condition. So
Wait, sorry. Is this also a finish of the upper bound? Or is there?
yeah, this was the upper bound, right? The lower bound just came from, I think it was on the board that I just deleted. It was just this tripartite, complete balanced tripartite graph.
Oh,
And then for so all this was the upper bound, right? So we assumed that we had this this H which on n vertices with so first we argued that if we are free of the B and the K4 minus, then we can assume that every triple must be incident to many edges, because otherwise we could proceed by induction. And that, together with assuming that we're K4 free, gave us the contradiction when we have more edges. So yeah, this observation for the minimum degree is given delta and epsilon larger 0 and some m0 k equal to 2. There's some n0 such that every K graph with on greater equal n0 vertices with the number of edges being at least delta plus 2 epsilon and choose k has a subgraph on m greater equal to this m0 vertices, which has minimum degree, essentially what the average degree that we expect from that. But we pay a little bit of the epsilon for it. Minimum degree at least that. Okay. So and let's just say the proof sketch. And let's just iteratively remove vertices which have too small degree. And then you have to note, but that just follows because our n0 can be much larger than m0. So when we remove vertices of too small degree, because we have this little gap between the epsilons, or between this 2 epsilon and epsilon, so we will keep the right density, but we will even put a little bit of epsilon aside. But if we put that epsilon aside, when we still had n vertices, that number of edges, once we've gone down to m0, will be much larger, so that we know that the process needs to stop. Okay. So let's now look at the next K-graph for which we want to determine the Turán density. And this so-called F33. So F33 is defined. Okay, so we have 6 vertices. A, B, C, D, E, F. Let's say A, B, C, X, Y, Z. And the edge set is on the one hand our ABC, and then on the other hand all 3 edges which intersect ABC in one vertex. So E and okay, so how does this one look like? We have one edge, and then we have these 3 vertices, and we have all edges of this type, which have 2 vertices in the bottom and 1 in the top. And the Turán density of this is 340. You can combine it. So for the lower bound, let me just draw it. So we take 2 sets of size roughly n², and all edges which look like this. And then you can check that this one has density 3/4 and does not contain our F33. For the upper bound, epsilon given, and the H. So by this observation, we can now assume that we have a minimum degree condition. The graph on n vertices with minimum degree at least 3/4. That's epsilon times edge scale. Minus 1. Oh, sorry, this is just 2. Okay, so because of this, we can always just go to a subgraph that has that minimum degree. And since we can make the n as large as we want, we can assume that we start with it. And okay, so now we want to make, in some sense, a similar argument, right? We want to say that if we have some edge, and then here we have it, we see in their link a triangle such that each of these edges appears in the link of each vertex here, then that would give us exactly our copy, right? Because here we have an edge, and each of the vertices in the edge sees to the other side a triangle in the link. So, but maybe we cannot quite find that. So, because we sort of, there's no room for error. So to introduce a little bit of room, we can say, okay, let's, instead of looking at an edge here, let's look at a 3 uniform K4. And then we just need that for one of the 4 edges, we see all edges in the link. Okay, and that gives us a little bit of room that allows us to finish. So first, recall that, so we showed actually that the Turán density of the K4 is smaller than 2/3, but you can also just say that this is at most the extremal number on 4 vertices divided by what you see, and this is important. Okay, because we have this monotonicity argument. And so there's some K4 in H, say on vertices B, C, D. Now consider a weight function. So just a map onto the remaining vertices, and we want to from the remaining vertices, and we want to map for each of the pairs. We want to map it to the multiplicity that it has with respect to the links of these 4 vertices. So let's say from V minus A, B, C, D to 0 up to 4. Oh, sorry, and this choose 2. Yeah, so all the 2 subsets. Where x1 gets mapped to the number or 2. Slide it to the number of alpha in ABC D such that XY is an edge that link. Okay. And so we are done if we find some x, y, z with the weight on that x, y, z, by which we just mean the sum of the weights on all the pairs in this set, if this is at least 11. So why is that? What's the possible way that we can have here? So we have 3 pairs, and on each we might have at most weight 4, so it would be 12. So this means that there's just one of the pairs in the triangle and one of the vertices in our K4, such that that vertex does not have that pair in its link. But then we just take the other 3 vertices, and each of them has all the 3 pairs in its link, and that gives us our F33. So, and this follows from this lemma. So we have a certain number of because of this minimum degree, we know that how much weight we have in total, right? Namely, we have 4 times essentially this. We subtract a little bit because each of the links also sees 3 edges on the K4, but because we have the epsilon room that won't. And so what this says is that if this from n to 0 up to 4 is weight function with the weight on every ijk being at most 10, then the total weight is at most n 2n choose 2 plus 2n squared over 4 about. So this is actually also best possible, as you can see when you take again and half vertices here, and on all these pairs you put weight 2, and on these pairs and here also weight 2, and here you put 4.
The function is n or n to 2.
Sorry, yeah, choose 2. Thanks. And okay, so with this, if we now know that the total weight here is 4 times this, so roughly we have 3 times n choose 2, but a bit more than 3 times n choose 2, and this thing here is essentially 3 times n choose 2. So by the min degree condition, above we have that the total weight on the C D is at least 4 times 3/4 plus epsilon and choose 2 minus, again, each of the vertices sees 3 edges in the K4. And so it follows with this lemma. And maybe let me just mention, because the proof of the lemma is actually also quite short and simple. So we do an induction on n, and then one case is that we never have any pair on which we have weight 4. Then it just follows by counting that we have less than that total weight. And if we have one edge of size of weight 4, so we have one pair on which we have weight 4, then that means that for any other vertex, when we look at these 2 edges, the sum of these weights is at most 6, because in this triangle we have at most weight 10. But then we can delete this this pair, and we don't delete that much weight because in total we sum for every vertex at most 6, right? Plus this one vertex, and then induction gives that that we are below the bound. Any questions?
I mean, we may assume there's no edge of good form.
Yeah, I mean, but also if there's no edge of weight 4, then the total weight will be less. And if there's an edge of weight 4, we can delete that edge and then finish by induction. Yeah, it's just about the phrasing, right? Like, do we assume that we?
And this lemma is in this weird form or in the more general form? The 4 and 10.
So I mean, definitely there's a much more general version than this by Firelli and Künken, which can then be used, for instance, for a very similar argument for the final plane. Yeah, but I'm not sure whether this original lemma might just be like that. I think also these kind of problems are interesting by themselves, right? They are basically another variant of Turán, where you just say, okay, instead of having some number of edges, you have some total weight, and now which kind of configurations of weights can we forbid? Any other questions?
So wait, I'm a little bit slow. So the weight of what you mean is V minus A, B, C, D choose 2, right? The pairs there, or you.
Oh, so when I write this, I just mean the weight of all pairs on this set. Right? Like also here, I mean
Right.
the weight of this of all the edges in the triangle.
So for every pair, we know it. So why is at least that?
So because that essentially just counts how many edges are in the links, but we count it with multiplicity, right? So we take the vertices A, B, C, D, and for each of them we place its link, and that sort of adds the weight of every pair that appears in the link by 1. And then so that means that this total weight is just the sum of the edges in all the links. Yeah, we could also formulate it as some sort of multigraph, right? And then we count the edges in that multigraph.
Yeah. Any other questions?
So there is anything wrong on the last board, like the first line says that we want to find XYZ with the weight with its weight being bigger than 11. But weight is defined on 2 sets of V minus ABC.
No, but this is what I said, right? Like whenever I write here just a set, like also here, then it means all the sum of the weights of all the pairs in that set.
Okay.
It's just a shorthand notation to not always write the sum.
So basically today what we're seeing in a nutshell is to reduce it to a weighted Turán problem in a link, right?
In some sense, yeah. And there's another example. Maybe I will then mention it tomorrow, which which does the same thing for the Fano plane. So they can also do that. And yeah, so definitely, I mean, this makes these kind of problems doubly interesting, right? Because they might be helpful. And I think, yeah, also, so the key thing here was also that by taking out more than what we are actually looking for, that allows us to give some room, right? You could imagine that for some problems, of course, then the density would have to be very large, but maybe taking out a K5 would give us even more room to play with. And yeah, but I should also say that actually for this Bolivar's theorem, there's also a very in some sense very different proof, where you just count the pairs, and then you sum over all the pairs, and that double counts the edges. And because you know that this Bolivar's graph is forbidden, so you can sort of get an estimate on the degrees of pairs.
So final plan just just F34, right? In this notation, final plan is
Yeah, I mean, yeah, I didn't exactly explain what the what this notation or how it generalizes.
So for F33, is there some general result about some graph looks like this one? If we change the 3 vertex to some set for other sets.
That there's a general result?
Yeah, like F3T something like this. F3T.
Okay.
If is near some result.
I mean, I don't know, but I mean, I could imagine that there's some bounds, but I don't know. I should also mention good, because of course we will just go through some examples, and there's this paper by Balog, Kleeman, and Lidicki, where they have a big table with more or less all known results from different variants of the Turán density.
Okay, then let's thank Bjarne.